Example. Find the tangent line to the implicit curve x times y to the power of 2 plus e to the power of y minus 1 equals x to the power of 3 plus y minus 6 at the point 2, 1. We find tangent line exactly the same as if the function is written explicitly. We have to find dy dx, so we get the slope. After, we will substitute the point in. The point means that x equals 2 and y equals 1. And we also have a point. And if we have a slope of a point, we can get a tangent line. So first we differentiate. The first one is the product rule. And we get y to the power of 2 plus 2y times dy dx times x. The second one is just one of the building blocks, and we get e to the y minus 1 times dy dx. And then we differentiate x cubed, we get 3x to the power of 2, and then the derivative of d dx of y is dy dx. And d dx of 6 is 0. We're done with differentiating. We have now to solve for dy dx. All those terms are containing dy dx. So I put all of those in one side of the equation and the rest on the other side. Now I'm going to distribute dy dx. I get that, and now I'm doing the division. After I find dy dx, I can substitute the point to get the slope of the line. Let's do that. We are going to substitute 2 for the x and 1 for the y. We get 11 over 4. For the tangent line, the slope is 11 over 4 and the point is 2, 1. We'll use the point slope equation of the line and we get this. In this case, it is possible to find the slope in an easier way. This is useful only if we don't need to find dy dx as a function. So here I'm going to show you an easier way, but again, if only you really don't need to find dy dx as a function, but just as a number. First we differentiate as before, and we get this exactly as before. But here is now the trick. It's much easier to find dy dx if you substitute first the point x equals 2 and y equals 1. The algebra is just much easier. So I'm replacing all the y's by 1 and all the x's by 2. And I get that. Simplify the algebra. In this case, you can see that you can cancel the dy dx both sides, and you're left only with 1 plus 4 dy dx equals 12. So 4 dy dx equals 11. And dy dx equals 11 over 4. As you can see, this is much easier to do. Now, as usual, we can do this really fast because we did it before. And we get, obviously, the same line because we got the same dy dx. Second derivatives of implicit functions. We are going now to show an example to learn how to do that. We are going to use implicit differentiation to find the second derivative of 2x cubed minus 3y to the power of 2 equals 7. I would like to recall that the second derivative is the first derivative of the first derivative. So first we have to find dy dx. We know how to do that. We get that. We're going now to solve for dy dx, and we get the dy dx equals x to the power of 2 over y. Now we have to find the derivative of the first derivative, which means that we have to differentiate now the dy dx. So what is d dx of x to the power of 2 over y? For this we will need to use, in this case, the quotient rule. We differentiate the top, we get 2x times the bottom times y, minus differentiate the bottom, we get dy dx times x to the power of 2 over the bottom function to the power of 2, which is y to the power of 2. If you notice, this derivative contains dy dx. So now I'm going to substitute x to the power of 2 over y for dy dx. I get this. I'm done with differentiating. The only thing that we like to do now is simplify this expression. And when we do, we get that. Example: use implicit differentiation to find the second derivative of e to the power of xy equals 3. First we have to find dy dx. On the left side we will have to use the chain rule combined with implicit differentiation. The outer function is e, so we get e to the power of xy times the derivative of the inner function xy, and for this we will have to use the product rule, and we get y plus x times dy dx. On the other side we get d dx of 3, which is just 0. We have now to distribute the e to the xy, because in the parentheses we have y, which does not contain dy dx, and x dy dx, which does contain dy dx. Now we are ready to find out the dy dx is negative y e to the xy over x times e to the xy. We can cancel the e to the xy, and we get the dy dx equals negative y over x. Now we have to differentiate negative y over x. Again, this is a quotient rule, and we get that. The quotient rule, as before, also contains the dy dx. So what I'm going to do now, I'm going to replace that by negative y over x. And I get that. Only thing left to do is simplifying. For example, I can cancel the x in negative y over x times x. And I get negative y plus y, which is 2y over x to the power of 2. Example: differentiate fx equals a to the power of x using the fact that d dx ln of x equals 1 over x. We will call fx the function y, so y equals fx, so y equals a to dx. We are going to apply the inverse for both sides, and we get that log base a of y equals x. Now I'm going to use change of base. If you recall, log base a of y can be also written as ln of y over ln of a. And I get ln of y over ln of a equals x. Please be careful, ln of a is a number, just a constant. That's why I can distribute that and get 1 over ln of a, which is just a constant, times ln of y equals x. It's time now to find dy dx using implicit differentiation. d dx of ln of y is 1 over y times dy dx, and d dx of x is 1. We get that dy dx equals y times ln of a. The only thing left to do now is to replace y by a to the power of x. And I get that dy dx equals a to the power of x ln of a. dy dx is the derivative of the function fx. I would like to know that in the special case when a equals e, we get the dy dx of e to dx is e to dx times ln of e, but because ln of e is 1, this is just e to dx. There are two main applications to implicit differentiation. First of all, it's logarithmic differentiation. And second, it's using the derivative of a function to find the derivative of its inverse function, if exists, as we did in the previous example. Each one of these applications is in a separate section.